even and odd signals. Another set of useful properties of signals led to the symmetry under time reversal. Time reversal. A signal x of t or x of n is referred to as an even signal if it is identical to its time reversal counterpart. That is reflection about the origin. Reflection about the origin. Reflection about the origin. Say available from the origin. What is the say? Time reverse. Time reverse. This one, this one. But time reverse. It's reflection about the origin. In continuous time signal is even. In continuous time signal is even x of t, that is x minus of t equal to x of t. Here this is x of t. Here x of t, x of minus t, that is, for example, here x of minus t, here equal to x of plus. That's why even. Signal is even. While discrete time signal is even if x of minus n equal to x of n. Here x of minus n equal to x of n. Here this is x of n, this is x of minus n. So equal same. Here n is less than 0. This is height. Here n is greater than 0. This is 0. Yeah, signal referred to as odd x of t, x of minus t equal to minus x of t. X of minus t equal to minus x of t. That is x of minus t. This is x of minus t equal to minus xt. Minus xt. That is x of minus n equal to minus x of n. X of minus t, this is minus t, equal to x minus xt. That is here xt, not here. Here xt, x minus t, x minus t. Here this is x of t. Here x of minus t. So in this way, at the time of t equal to 0, here x of minus t equal to minus x of t. X of minus n, here in our signal, x of minus n equal to x of minus n equal to x of minus x of n. That is An odd signal must necessarily be 0 at t equal to 0. An odd signal must necessarily be 0 at t equal to 0 or n equal to 0 in odd signal. In odd signal t equal to here only 0. So since equation 1.16, 1.17 require that x equal to x of 0 equal to minus x of 0. That is here 0. So x of 0 equal to minus x of 0. Here same. And the x of 0 here also for this equation also same. X of 0 here. X of 0 0 same. Here also same. Examples of even and odd continuous time signals are shown in figure 1.17 here and even continuous time signals. And here what is available in the negative side, same available in positive side in the time reversal. That is, this one started here, this one here ended. This start, this end. So what here start, that one start. Starting from, actually here start from here to like this. But here, from start from here itself. What end can start. This is only end, no? So the start like this, end here. This is here, this is start, this end. In negative side. In positive, this is start, this is end. That is mirror image. And B add continuous time signals. Here, 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 this is started like this. After that, here signal not like this, not like this. Here, then this one going like this. So here minus, here in plus. Here this is in minus. In T is the minus. T is the here plus. Here T is minus. T is this side plus. But this one not happening here. Here happening. So total negative. So here total positive. So different entirely. But here this is immer image. Only. So add continuous time signals. Add this one here started, here ended. After that, here totally negative value. Here totally positive value in positive time. Here totally negative value in negative time. So this one here, this one here in positive, this one here in positive, this one here in positive, this one here in positive. Here, this one here, this one also positive, this one also positive. Like this one also positive, this one also positive. But here entirely different. That's why here problem. Here totally negative. Here totally positive. Here totally in positive only, but amplitude. Here also same like that. In discrete time signals, examples of the even or decomposition of a discrete time signal. examples of a even odd decomposition of a discrete time signal. Y is a n. Okay, in exactly. This is 0, 1, n equal to 0, n equal to 1, n equal to 2, n equal to 3. N equal to minus 1, n equal to minus 2, n equal to minus 3, and so on here. Up to negative infinity. Here, going to positive infinity. Okay. Here, x of n equal to 1. When will come 1? N is greater than or equal to 0. Here 0. Here 0. Greater means here full here greater. Okay. So this time x of n. This is the x of n. Okay. This is x of n full 1. Okay. X of n when will be 0? Condition is that. So x of n here is 0. When n equal to less than 0. Yes, or n is less than 0. It means after 0 here all are less only. So n less than 0. So this condition only here 0. Here open, here close the condition. Okay. And here in this figure, even in this is even signal, this is odd signal. In this even x of n equal to condition n is while of 1 by 2, n is less than 0. N is less than 0. This is 0. That is x of n equal to 1 by 2. Okay. When will be 1? This is off. This is 1. Okay. Up to here off. Then 75 1. Okay. Here 25 like this. So when n equal to 0, this is 0. Okay. That is 1. X of n equal to 1. When n is greater than 0, this is 0. This area full greater than 0. 1, 2, 3, 4. Less only this side, left side. In right side greater than, n equal to 0 only. Sorry, n is greater than 0. Here n is greater than 0. So n is greater than 0 time. This is 1 by 2. So less than time 1 by 2. Greater than time 1 by 2. This is even. Okay. Yeah, whatever happening here, same happen. Okay, like this. So from here, this corresponding or this corresponding minus 1 plus 1, minus 2 plus 2, minus 3 plus 2. What is happening? Minus 3 plus 3 here happening. Here odd the set of x of n equal to 1 by 2 minus 1 by 2. The condition is n is less than 0. Here minus 1 by 2. Okay. When 0 x of n equal to 0, when n is condition is n equal to 0. So 0. 1 by 2 will get when under another condition. When 0 is greater than n. When 0 is greater than n. It means when less than 0 full available here. 1 by 2 minus 1 by 2. When greater than 0 here full available. N is greater than 0. So while 0 n equal to 0, that time only 0 available. An important fact is that any signal can be broken into sum of two signals, one of which is even and one of which is odd. To see this, consider the signal